Schwartz, the unsteady thin airfoil theory, and Peters. And now we are about to study the flutter, which is a very practical topic, very interesting. So this is solid mechanics. Structure, sometimes we call structure. Structures. And this is aerodynamics. And this is dynamics. And you tell me if we have aerodynamics and dynamics. This is blue and red, maybe something like aerodynamics and dynamics is what? Those are two.
175.
Yeah. So it's what? Aerodynamics plus dynamics is what? If you combine aerodynamics and dynamics, you get what?
What, as in like in terms of application or in terms of?
You get what discipline in science?
Flight mechanics.
Flight mechanics, so flight dynamics. This is flight dynamics, which is the title of the course 175. Flight dynamics, okay. And if you combine aerodynamics and structures, what do you get? Aero and structures. Aero and solid mechanics. There was a course under that name last, I guess, fall or something. Aeroelasticity, right? Remember solid mechanics or structural dynamics, sometimes it's called theory of elasticity. So if you combine aero and elasticity, it's simply aeroelasticity. And if you combine structure and dynamics, what do you get? Structure and dynamics, what do you get? Any suggestion? It's very simple, it's structural dynamics.
Okay.
Which is equivalent to, or sometimes as another name, vibrations. Right? And this very interesting piece, right here, this is dynamics. So this piece, the green piece, has all the disciplines, right? Has all the three disciplines. It has dynamics, it has structure, it has theory of elasticity in it, and it has aerodynamic loads. So depending on the dynamics of what? Usually it's dynamics of a flying vehicle or a flying wing. If it's dynamics of a flying, the whole flying vehicle, so this is dynamics of flexible airplanes. Which is very interesting. You can say flight dynamics, but it doesn't matter. If you're only concerned with just a flying wing, it's not the whole airplane. So sometimes we call it dynamic aeroelasticity. So aeroelasticity, the branch of aeroelasticity, which is very, very interesting. There are some new phenomena emerged due to the interaction between the aerodynamic loads and structures. So these phenomena, there are some of these phenomena that belong to static aeroelasticity. They're just static phenomena. But some other of these phenomena, they are dynamic in the sense that there is motion. So under this branch, dynamic aeroelasticity, there is the flutter phenomenon, which is beyond a certain speed, the wing simply flutters. And I'll show you, I guess I already showed you a video in the in the first lecture about this thing. No. You can see the wing flutters. So if the airplane exceeds a certain speed, the wing starts to flutter, moves up and down, and twists up and down. So combined pitching plunging in our discussion, or combined, from a structure point of view, it's combined bending and torsion. They call it bending torsion flutter actually. So we showed this in the,
Sure.
yes.
Is it like also twisting as well? If it's torsion, so it's also in that case, or like it's just
I'm sorry, say it again?
like if it's like torsion, then it's also like if it's like bending, but then if it's torsion, then it's like twisting as well in that case.
Yeah, yeah. We'll talk about it in a minute. So this is our topic today. We will analyze Flutter, which, like I said, it has the three disciplines. We need to write a dynamics model, structural model, and the aerodynamic model. Of course, we will start with the simplest of each discipline, or maybe the most relevant to this course. Some of them will be trivial or very simple. But this is our topic today. We want to compute at what speed flutter phenomena will occur. Okay? Any question with that? Any question? Okay, just reminding you that when you have an airplane like this, okay. Remember we have, so this is the wing. So there is a distributed lift force all over the wing, right? So anybody remembers the shape of this distribution? What's the optimum shape at least? I'm sorry? Elliptical. Exactly. So there is a very large force near the root, and it goes to zero near the tip, and it has an elliptical shape. This is the optimum shape for minimum induced drag, but it's not optimal with respect to the root bending moment. It creates a large root bending moment. For us, so this is pure aerodynamics. You look here, okay, here is a wing. The lifting line theory will give you this distribution. Pure aerodynamics. Now, from a structural point of view, this guy is a beam. This wing is a beam. It's a cantilever beam. And if you're pushing it forward with a force and it's fixed here, it will deflect a little bit. Right? So this guy will deflect like this. And this is a structural deflection delta. And here is maybe the resultant aerodynamic load, the total lift force, F. Okay? So the aerodynamic aspect of it is that given the geometry of the wing, it will give you this, how much lift is generated. The structural aspect of it is that given the applied load F, it will give you the structural deflection delta, right? And yes, there might be a complicated relation, but at the end of the day, it's as exactly abstract as the force is proportional to delta, right? And this proportionality concept might be complicated, has EI, bending rigidity of the beam or whatever, but the delta at any station Y is proportional to the applied load, okay? So as you can see, it simply can be represented in an abstract form like a spring. It's as if this wing is attached to a spring in that direction, so that when the lift force drive pushes up, the spring returns it back. But because there is a non-zero force, there will be a non-zero displacement of the wing. And this displacement is quite large. Actually, here is another figure. You can see here, this is Boeing 787 Dreamliner. So this blue curve is the neutral shape of the wing. In flight, you have 10 feet deflection of the tip. This is really large bend, right? It's like 3 meters, so larger than the height of this room. And if it's 150% maximum load, this is 26 feet. It's a huge, huge deflection. Okay. This is the deflection I'm talking about here. Okay? Any questions so far? Any question? Okay. Another view of it. Have your wing like this. So the aerodynamics produce forces, lift force, distribution of lift forces, right? Becomes smaller and smaller. But also what? When you have an airfoil, you have lift, what else?
Drag.
Drag, and what else? Lift, drag, and the triplet is what? Lift, drag, and what? Pitching moment, exactly. So you have a pitching moment. You might have the same distribution. So if you look, so again, this is a cantilever beam, right? And if you have this kind of moment, which is from an aerodynamic point of view, it's a pitching moment. Now, from a structural point of view, it's called what? Twisting moment, exactly. So this lift distribution bends the beam or the wing, and this moment distribution twists the beam or the wing. So the side view, this is the core, this is your airfoil, and if it rotates about some point, then here is the new core, and here is the new airfoil. And this angle is the structural deflection angle, say theta, due to the applied pitching moment M, and the relation again is as abstract as just spring. Okay? So the aerodynamic loads try to twist the wing, and because the wing has some flexibility, it has to, so it will really twist a little bit, some angle, and the relation for a small disturbance is linear. If you apply more moment, if you double your moment, the angle will double. Okay? Any question about that? Yes, Leo?
But in flight, don't you just extend the airplane so there's no Cm, where Cm equals 0?
Cm equals 0 where?
Equal.
No. Cm equals 0. What is the condition for trim? Cm equals 0 where? At the CG. So at any other point there is a moment. So at the end of the day, this is at any two-dimensional section, there is lift and pitching moment at the aerodynamic center. The transfer of all these moments at the CG, in addition to the trim moment coming from the tail, they must balance each other. But if you look at the wing on its own, no, it has a non-zero pitching moment. Okay? So this is the reason for having the tail, is to balance the moment coming from the wing. Okay, so this is the picture that we have, and you can easily deal with the structure in with this flutter problem in a three-dimensional sense. We can use Euler-Bernoulli beam theory, which you already studied in your undergraduate, to study the structure of the wing. And we have Theodorsson, theory unsteady aerodynamics, to study the unsteady aerodynamics of it. And the dynamics is not that difficult. Force equal mass times acceleration, and you combine the three models. But we will not focus too much on structure. You can do that in a course that is focused on aeroelasticity. This is not an aeroelasticity course, this is an unsteady aerodynamics course. So we will take the simplest model in any other discipline. Remember, here are the disciplines, aerodynamics. We will try to be here as precise as possible. For structure and dynamics, we will take the simplest models. And as you can see here, no matter how complicated your model is, in fact, really in the small deflection region, the relation is linear and whatever theory you're going to use, Euler-Bernoulli or whatever, it will just give you a value of this constant. So to me, at the end of the day, it's a spring with some constant. And the structural theory will give you the value of this constant depending on the geometry and rigidity of the beam. This is not my concern. So for me now, we will do something called like a typical section analysis. By typical section, we mean we will not consider three-dimensional structure. We will just consider two-dimensional. So here is your wing section. So we consider just an airfoil. Usually we take this airfoil to be at a 70 to 75% of the span of the whole wing. So some section here. This is the typical section we're considering. So half code point. Where is the lift located? Where do we like to locate our lift? Where do we typically locate our lift?
The foil point.
Yeah, very good. So call it the aerodynamic center. Lift, and at this point there is what? There's a pitching moment at the aerodynamic center. It's constant, it's not zero. So when we have twisting like this, when you have both bending and twisting, so each of these sections, this section, moves up a little bit, bending, and also twist. It twists about what point? Do you remember a twist about what point? Structural theory. Do you remember from your undergrad? Did you ever hear this thing? Shear center? Did you compute shear center before? No? Yes? So anyway, we'll not consider that, but at least we know that when we have a section, there is a point about which the rotation occur, and if you analyze at this point, then bending and torsion are decoupled. You can consider them as decoupled. Otherwise, bending will affect torsion. The shear center for each section. So maybe this is the shear center for this section, this is for that section, this is for this section, and so and so. And if you connect all these guys, this is what we called what? Do you remember? From your undergrad, again, we'll not rely on it, but it's good to refresh our memories. It's the elastic axis. Okay. So if you have a symmetric section, so like a rectangle or something, the shear center is the geometric center, it's in the middle, but the airfoil is not. It's not, it's not a symmetric section. So to determine the value of this guy is non-trivial, but you can use any of the off-the-shelf software like Nastran. It will tell you the shear center for a given airfoil. And I guess they are tabulated online. NASA 0012, you can go and look